Hey everyone, welcome back to the channel. Let me start with a quick question. Have you ever opened a statistic page or stared at a screen full of numbers in SPSS and just thought yourself, okay, but what does any of these actually mean? If that is you, then you are in exactly the right place. In this video, we are gonna walk through one of the most useful toolkits in all of quantitative research. It is called parametric analysis. And by the time we are done, you are gonna comfortably understand three big ideas. First, how to measure whether two things move together, which we call correlation. Second, how to use one thing to predict another, which we call regression. And third, how to actually run all of this yourself, click by click, inside SPSS. Here's my promise to you. I'm not gonna bury you in formula. We are gonna use plain language, real intuition, and a few simple pictures. So whether you are a doctoral student polishing a dissertation or just someone curious about how data really works, you will be able to follow every step. No prior statistics background required. If you can read a chart, you can do this. So grab a coffee, get comfortable, and let us get into it. So let's start with the obvious question. What is parametric analysis really? Here's the simplest way I can put it. Parametric analysis is a family of statistical tests that assume your data follows a known predictable shape. And almost always, the shape is the famous bell curve, the normal distribution you can see right here on the screen. Think about it like this. If you measured the height of 1,000 adults and plotted them, most people would land somewhere in the middle, close to the average, and only a few would be unusually short or unusually tall. That pile in the middle, seen on the edges pattern, is the bell curve. Parametric tests assume your data behaves roughly that way. Now, why does this matter? Because when your data plays by those rules, these tests are genuinely powerful. They work with numbers measured on a real scale, things like income, age, test scores, or years of schooling. They let you estimate true values in the whole population, like the average and the spread, and they give you precise results, confidence intervals, and effect sizes, the really useful stuff. The big names in this family are ones you have probably heard of already. The t-test, ANOVA, Pearson correlation, and linear regression. Those last two are our main characters for today. So here's the headline. When your data is well behaved and measured on a real scale, parametric tests give you sharper, more confident answers. But, and this is a big but, that work too is doing a lot of quiet work. So let us talk about when those assumptions hold up and when they fall apart. Is parametric versus non-parametric. Because here's the thing. Parametric tests are not always the right tool for the job. Sometimes you need their cousins, the non-parametric tests. So how do you decide between them? Let me put them side by side. On the left, parametric tests. They assume that normal bell-shaped distribution we just talked about. They want continuous data, real interval or ratio numbers. They summarize everything using the mean and the standard deviation. And when their assumptions are met, they have more statistical power, which simply means a better chance of catching a real effect when one is actually there. This is your t-test, your ANOVA, your Pearson correlation. On the right, the parametric test. These make no assumption about the shape of your data at all. They are perfectly with their rank or ordinal data, like survey answers that run from strongly disagree to strongly agree. They lean on the median, on ranks instead of the mean, and they are tough. They hold up well even with small samples and with messy outliers. Names here include Spearman's correlation and the Mann-Whitney test. So, what is the rule of thumb? Honestly, it is refreshingly simple. If your assumptions are reasonably met, go parametric because you get more power and richer results. If those assumptions are clearly broken, switch over to non-parametric. The whole game is matching the test to the data you actually have, not the data you wish you had. Want to see assumptions for parametric tests? All right. Now, one of the most important topics in the entire video, so stay right with me. If parametric tests lean on assumptions, then we had better know exactly what these assumptions are. These are basically 8 things you want to check before you trust a parametric result. Number one, normality. Your data, or more precisely, your model's errors, should be roughly bell-shaped. Number two, interval or ratio data. Your variables should be measured on a real numeric scale, just sorted into categories. Number three, independence. Each observation should stand on its own and not be secretly tied to the others. Number four, linearity. The relationship you are studying should follow a roughly straight line pattern. Number five, homoscedasticity. I know it's absolute master of a word. It just means the spread of your error stays fairly even across the whole range of your data. We will actually see a picture of that idea a bit later. Number six, no severe outliers. A couple of extreme points can throw everything off, so you check for them and you deal with them honestly. Number seven, an adequate sample size. Bigger, carefully collected samples give you more measured accurately and consistently with as little error as possible. And here is a friendly tip that ties all 8 of this together. Before you run a single test, just look at the shape of your data, plot it. A quick histogram or a simple scatter plot will tell you more in 5 seconds than a whole page of numbers ever could. Check the shape first, then choose your test. Did you say the core pillars? Now, before we go any deeper, let me hand you a map of where we are. Because everything in parametric analysis really comes back to a small handful of core ideas. Picture them as the pillars holding up the whole structure. We have got the assumptions, these conditions we just covered that keep our results valid. We have variables, the predictor and the outcome, the two things we are relating to each other. We have the distribution, the normal curve sitting underneath it all. We have correlation, which captures the strength and the direction of a relationship. And we have significance, which tells us how big a role playing chance is playing in our findings. Then we have effect size, which tells us not just whether something matters, but how much it matters. We have prediction using our model to estimate outcomes within the range of our data. And then it all loops right back around to those assumptions. Hold this picture in your head because for the rest of the video, we're gonna zoom in on the two pillars that do most of the heavy lifting in real research. Those are correlation and regression. So let's start with the correlation. Let's start with correlation. So correlation, that is very hard. Correlation answers one beautiful simple question. When one thing changes, does the other thing tend to change along with it? The tool we use to measure this is called the Pearson correlation coefficient. And we write it as a single little letter R. Then here's the elegant part. That R value always lands somewhere between -1 and +1. That is the entire scale, end to end. Let me unpack what the actual means. A positive R means the two variables rise together. As one goes up, so does the other. In our studied and exam scores. A negative R means they move in opposite directions. As one goes up, the other comes down. Think hours spent scrolling on your phone and, well, those very same exam scores. You start to see this stuff everywhere once you go looking for it. Exercise and resting, heart rate tend to move in opposite directions. Years of experience and salary tend to climb together. And or sitting near zero, that tells you there is a little to no straight line relationship at all. The two just are not really cracking each other. But here's the move that separates the careful analysts from the sloppy ones. Before you trust any correlation number, you look at the scatter plot. You let your known eye see the pattern in the cloud of points first. The number gives you a tidy summary of the story, but the picture is what tells you whether that story is even the right one to be telling. Let's do interpreting R. Okay, so we know that R runs from -1 all the way to +1. But how strong is strong, really? Let us put some actual meaning onto the scale. Picture a ruler stretching from -1 on the far left to +1 on the far right, with zero sitting right in the middle or at the very edges, close to plus or -1. You have a very strong relationship. The points line up almost perfectly. As you move inward towards something like plus or minus zero point 0.5, you are looking at a moderate relationship. And as you drift in close to zero, the relationship gets weak and eventually it fades into nothing at all. Now, here's a sail point that trips up an enormous number of people. So let me slow down. The sign and the size of R are telling you two completely different things. The sign plus or minus tells you the direction. Do they move together or in opposite directions? The size, how far it sits from zero, tells you the strength. How tightly do they actually track each other? So a correlation of minus zero point 0.8 is exactly as strong as a plus zero point 0.8. They are equally high. They just point opposite ways. Here's a quick way to sanity check yourself. If someone tells you they found a correlation of zero point 0.9, picture points hugging a line very tightly. If they say zero point 0.1, picture a vague, shapeless cloud. Train your intuition to see the number as a picture and you will rarely be fooled. And one more handy idea to tuck away. If you take R and you square it, you get the shared variance, the silence of one variable that the other one can account for. Hold on to that because it is going to come right back when we talk about regression. And as always, pair every correlation with a scalar plot. The number all by itself can absolutely fool you. Is bivariate linear regression. All right. This is where it gets genuinely exciting because now we level up. We go from just describing a relationship to actually using it. This is regression. Here's the core idea. Correlation tells you that two things move together. Regression takes one big step further and it lets you predict one variable from the other. We take a predictor, our X, and use it to estimate an outcome or Y. Let me make that concrete. Imagine you run a little coffee shop and you have noticed that on hotter days you sell more ice drinks. Correlation all on its own would just tell you those two things move together, but regression lets you say something far more useful. For every 1 degree the temperature climbs, you can expect to sell roughly this many more iced coffees. And just like that, you can plan tomorrow's inventory straight from the weather forecast. That is the whole leap from simply noticing a pattern to actually putting it to work. And the way we do that is by drawing a single straight line through the cloud of data. That line gets captured by an equation, and please do not let it scare you because it is so much simpler than it looks. We write it as y hat equal d0 plus d1 times x. Let me translate that straight into plain English. Y hat, that is the y with the little head sitting on the top of it, is our predicted value. It is our best guess for the outcome. B0 is the intercept. It is just the value of y back when x is 0, the starting point of the line. And B1 is the slope. It tells you how much y changes for every 1 unit increase in x. That slope right there is really the engine of the whole thing. So how do we find the single best possible line? We use a method called ordinary least squares. That is a fancy name for a simple idea. It picks the one line that sits as close as it possible can to all of the points at the same time. And here's a neat little fact for the curious among us. In this simple one predictor case, the standardized version of that slope, which we call beta, is exactly equal to our old friend R, the correlation. They are genuinely two sides of the very same coin. And the payoff for all of this, once you have that line, you can estimate outcomes that you have never even observed. That right there is the quiet magic of regression. Now the line of best fit. So I think I've got this line of best fit. But let me ask the honest question. How do we actually know it is any good? For that, we need to talk about residuals. A residual is just the gap between what really happened and what our line predicted. Picture a single data point sitting a little bit above the line. That short vertical distance from the point straight down to the line, that is the residual. It is simply our prediction error for that one case. Now, the entire goal of the line of best fit is to make all of those errors as small as possible, taken together. To be specific, it minimizes the square vertical distance. So smaller residuals mean the line is hugging the data tightly, and that means a better fit. There's also a related number called the standard error of the estimate, and it basically tells you the typical size of those prediction errors in the actual units of your outcome. And this brings us to one of the most useful numbers in all of statistics, R squared. Remember a minute ago when we squared the correlation? Well, this is it. R squared tells you the share of the variation in your outcome that your model successfully explains. So if your R squared comes out to, let us say, 0.4, that means your predictor accounts for about 40% of what is going on, and the other 60% is down to other factors that you simply have not measured yet. And that's not a failure, by the way. Out in the real world, almost nothing is explained by a single cause. A model that honestly explains 40% of the picture can still be genuinely, powerfully useful. A couple of honest cautions before we move on. Watch out for outliers because a single extreme point can yank the whole line around and quickly distort your slop. And just remember the simple intuition: a good model hugs its point tightly. A weak one leaves them scattered all over the places. Let's take a closer look at reading the SPSS output. Now, let's make all of this real. When you run a regression in SPSS, it hands you back three tables. And at first glance, they can honestly look like a wall of intimidating numbers. But once you know exactly where to look, they tell a really clear story. So let me give you the guided tour. And honestly, once you have done this 2 or 3 times, your eyes go straight to the numbers that matter once, and all the rest just quietly fades into the background. The first table is the model summary. This is where you find R, your correlation, and R squared. They share all variance we just talked about. So right away, this little table answers the question, how strong is my model and how much does it actually explain? The second table is the ANOVA table. And please do not overthink this one. Its main job is to answer a single yes or no question. Is my model statistically significant as a whole? It is checking whether the relationship you found is likely to be real or whether it could just be random noise dressed up to look like a pattern. You will look for a significance value, and the value below 0.05 is the usual green light that your model is meaningful. The third table is the coefficients table. And this one is the real heart of it. This is where you read the actual numbers for your equation. The constant gives you that intercept, your B0. The P value for your predictor gives you the slope, your B1. There is also a standardized version called beta, which lets you compare different predictors on a level playing field. And every single one of them comes with its own significance test. So you know exactly which pieces are actually pulling their weight. So put it all together. The model summary tells you how strong it is. The ANOVA tells you whether it is real. And the coefficients table hands you the equation itself. Three tables and one clean story. So, how to run it in SPSS? Okay, theory is wonderful, but let us actually click through this thing. Here's your step-by-step recipe for running a bivariate linear regression in SPSS. Follow along and honestly maybe keep this slide handy for your very next project. But before you even begin, do a quick gut check. Make sure both of your variables are continuous. Make sure the relationship looks roughly linear. Make sure data is approximately normal. And take a second to eyeball it for outliers. The 30-second check saves you from a whole world of headaches later on. Now, the steps themselves. First, go up to the Analyze menu, slide down the regression, and choose Linear. Second, in the box that pops up, move your outcome variable into the dependent slot and your predictor into the independent slot. Just remember, the dependent variable is the thing you are trying to predict. Third, click the Statistics button and tick the box for estimates and for model fit. That makes sure you get those coefficients and your R squared. Fourth, while you are right there, go ahead and add the confidence intervals and the collinearity diagnostics for a more complete picture. Fifth, pop into the plots option if you would like to SPSS to draw your residual graphs for you, which is fantastic for checking those assumptions with your own eyes. And then finally, you click OK, you will sit back and you read those output tables in exactly the same way we just predicted together. And that is it. You have officially run a real regression. So let's bring it all the way home. We have covered a lot of ground today. In just this one video, you have gone from what even parametric analysis all the way to running and reading a real regression, and that is genuinely no small thing. So there are the habits that quietly separate a careful analyst from a careless one. First, always check your assumptions before you trust a parametric test. That is the foundation everything else sits on. Second, look at scatter plot before you report a single correlation coefficient. Third, when you report a regression, give people the slop, the R squared, and the real word about practical importance, not just whether it happened to be significant. And here's maybe the single most important one of all. Always remember that correlation does not prove cautions. Just because two things move together does not mean that one of them is causing the other. Keep your claims honest and keep them inside the range of the data you actually collected. And when one predictor only explains a small slice of the picture, take that as your cue that the real world is more complicated. And that maybe you need a few more variables in the story. Because here's the big takeaway. The one thing I really hope sticks with you after everything else fades away. Correlation measures the link. Regression turns that link into predictions. SPSS does the math. But your judgment does the science. Good analysis was never about proving a point you already believed doing it. It is about genuinely understanding what the data is trying to tell you. If this helped, these concepts finally click into place, do me a quick favor and tap that like button. It generally helps the channel move than you would think. Hit subscribe if you want more breakdowns. You will like this one. And drop your questions down in the comments because I do read them and I will do my best to answer. Thank you so much for watching. Take good care of yourself and we'll see you in the next one.